to dealing with something like, oh, an electron. Well, how so? Well, an electron is a really tiny particle of matter. I mean, in order for you to see the tennis ball, what has to happen? Well, photons have to hit the tennis ball, bounce back in your eye to let you know where it is. Make sense? Okay. The problem with seeing an electron is you have to hit the electron with a photon so it can bounce off and bounce back, well, not into your eye, but into whatever device you're using to see the electron, so you can see it. Make sense? Here's the problem. The moment the photon hits the electron, unlike the tennis ball, it causes the electron to go flying off in a different direction at possibly a different speed. So you may know exactly where that electron is at that moment in time, but now you have no idea where it's going to be next, because the photon that you use to see where the electron is has immediately caused it to change where it's going next. Does that make sense? This is known as the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that it is impossible for you to simultaneously, that is, for you to know at the same time, for you to simultaneously know the exact position and momentum of an electron. Guys, there's a real consequence to this. Listen carefully, because the semantics are important here. If you can't know both the momentum and the position of the electron at the same time, it is impossible for you to calculate the path of the electron. Now, an orbit is a calculated path, which means that we are no longer justified in claiming that electrons travel in orbits. Notice what I said. I didn't say that the electron didn't travel in orbits. I simply said there's no way we can justify saying that they do, because there's no way for us to ever verify that. You understand? So Heisenberg's work and his uncertainty principle does not disprove what Bohr is saying. It doesn't say, ha, that's wrong. It doesn't say that. It just simply says, there's no way you should ever make that claim because there's no way to ever verify it. We're not justified in claiming the electron travels in orbits because there's no way we can calculate its path. And orbits are calculated paths. You guys understand? So what's left to us? Well, scientists like Heisenberg and others like Max Born, they went ahead and looked at this and said, well, you know, the best thing we can really do probably is talk about the probability of finding an electron. And so rather than speak of the electron traveling in orbits, from henceforth, we are going to speak of the electron traveling in orbitals. I'm standing at my desk, Mary. All right. There's a reason why I'm up on the desk. I am warning you right here and now. And unfortunately, I can't save you all. Some of you will fall. I'm trying to, but it's just not going to happen. I know it won't, because it never does. There will be some that, and you'll get your test back and you'll go, oh, and do you remember when I was on the, oh, yes, you will, because you weren't listening to me carefully. Listen, there is a big difference between, that's why I asked you to repeat, Carrie. There's a big difference between the word orbit and orbital. So, in your essay writing, you need to be very specific about which term you're using. In your reading comprehension, you need to be very specific about whether I'm talking about orbit or orbital. They mean different things. You might be thinking to yourself, no, it's not the same thing. An orbit is a clearly defined, calculated path. So what's an orbital? An orbital is defined as a region of space where we have a high probability of finding an electron. So as opposed to a clearly defined path, an orbital is a region of space where we have a high probability of finding an electron. They sound similar, but there's a big difference between the two. What do I mean by that? Well, let's go ahead and assume that I have you out in the hallway with me, and we'll say this room represents an orbital. Okay, so our room in here represents an orbital for an atom. And to represent the electron, I'm going to use a tennis ball. Okay? Now, it turns out that the electron moves extremely rapidly. So I'm going to say tennis ball, that's your orbital. Ready, go. That tennis ball will start moving around within this orbital. And it moves so blindingly fast that you and I, out here in the hallway, we wouldn't see anything in the room. All we'd see is a fuzzy green doorway and fuzzy green windows. It would look like the electron, or that tennis ball, was occupying all space simultaneously at once. Okay? This should not be, this should be understandable. You have to understand your visual acuity, your ability to see things is limited. Do you know that the lights above you are going on and off 60 times a second? You can't tell, but that's what's actually happening. Okay? If you've ever been, if you guys have been in a room with a strobe light, you know how when it's going boom, 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 it's like sort of, and as it goes, ba, 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 you can move around. It's still hard, but it's easier. Okay? The faster it goes, eventually, it's so fast, you can't even tell, and that's what's happening right now. The lights are going on and off 60 times a second. Your eyes can't pick up that difference. Think of a propeller of a plane. Propeller of a plane only occupies this much space, right? But when it's spinning, baby, that thing is occupying all of that space as far as you're concerned. Okay, and if you take your two fingers and go like this, it's not going to be like you go, ow, ow. Okay, it's going to just be one ow as both fingers essentially simultaneously clipped off, unless you have matrix-like skills. Okay, all right. In which case, you might be able to avoid that sort of routine. Because the electron moves this rapidly, we sometimes will refer to the electron moving about in the orbital as an electron cloud. Okay, so sometimes you'll hear the expression electron cloud. It has to do with the fact the electron is just moving. It looks sort of like that. If we were looking at our doorway with fuzzy green, I could touch with this finger and I would feel the tennis ball. If I touch with these two fingers, I would feel the tennis ball. If I had Jacob out there, outside, with the window open, he would see fuzzy green. I'd say, Jacob, you ready? He'd say, yeah. I'd say, ready? Now. And we would both feel like we were touching the tennis ball at the same time. You guys understand? Okay, and this idea of an orbital is what we're going to be using in developing our new model of the atom. That's how we're going to be looking at it. It's not traveling in orbits, but in orbitals. Questions? The mathematical expression that you see on page 9 dealing with Heisenberg's uncertainty principle, you can disregard. You don't are responsible for it. I would expect you to be able to state Heisenberg's uncertainty principle, but I don't expect you to do it mathematically. Questions at all? Okay. Yeah. This brings up Schrodinger's work. And Schrodinger is the one who's responsible for our modern model of the atom. Guys, I should warn you right now, the first natural response when people hear about this model is by the time I'm done talking about it, they start to go, okay, my head hurts, get a good night's rest, yeah, you're definitely going to want a good night's rest. It's natural, okay, it's natural. So it might seem a little complicated at first, it's a natural reaction. By the time we're done, it all starts to fall in place and it's understandable. Schrodinger is the one who's responsible for the new model of the atom. It's called the wave mechanical model of the atom. You might recall I said wave mechanics is the branch of science and mathematics and physics that deals with looking at the wave-like nature of matter. Schrodinger said, you know, Bohr had to be on something. Oh my God, I mean, it works so well for hydrogen. It explains line spectra. Clearly, something was right, even if it didn't work for the other elements. I mean, we can't just simply discount that. But he did assume, he made an assumption, he assumed the electron was quantized with respect to energy. You know what, I'm not going to do that. I'm not going to do that. I'm going to go ahead and develop a model of the atom. But I like this part of quantum theory that Broglie was talking about, that matter could behave as a wave, the electron could be as a wave. Maybe that's the way we should go. Maybe we should treat the electron not as a particle anymore. Let's treat it as a wave and see where that takes us. I'm not going to make any assumptions. I'm just going to look at the wave-like nature of the electron. And so he based his model on the second quantum part of quantum theory, put forth by de Broglie, specifically that matter in motion, while it could be particle-like in nature, at other times it could be wave-like in nature. And really what he did was focus on that wave-like nature of matter, specifically the wave-like nature of the electron. I'm going to look at the electron and its wave behavior. And I'm going to look at the wave functions. You guys know what a function is? F of x? You guys remember functions? F of x is equal to x squared minus 2 plus 1. You guys know what I'm talking about? All right. So he looked at, there are wave functions. For instance, if I ask you to plot this line, you would be able to go ahead and do that, yes? Yeah. Okay. If I said plot this, y is equal to x squared minus 3, what plot would you get? A parabola, right? Okay. And if we do other things, we get more complicated shapes. You guys understand? All right. There are equations like this that govern wave behavior, and they're involved. The mathematics of this, guys, is beyond the scope of our course. I don't know if MIT is still doing it. I know that what they had at one point, one of the alums came back and let me know this. They said they had a course, I think it ran only a semester. It might have been a whole year, but I think it was just a semester, where all they did was solve Schrodinger's wave functions for the whole course. I mean, that's all they did that whole course. So this math is beyond what we're going to do. Instead, what we're going to do is look at where the mathematics led him. You guys understand? All right. It turns out that if you look at these wave equations that govern wave behavior of the electron, as Schrodinger solved these wave functions, it became apparent from the mathematics that the electron is quantized with respect to energy. He didn't assume it. He didn't assume it. The mathematics basically is shouting up, yes, yes, the electron is quantized with respect to energy, but not in just one way. See, with Schrodinger's, with Bohr's work, Bohr just assumed that the electron is quantized with respect to energy, but only in one way, whatever energy level the electron was in. It turns out that the electron is actually quantized with respect to energy in 3 ways, and later we found out in 4 ways. So the electron is quantized with respect to energy in 4 ways. What does that mean? Well, it means that you need 4 pieces of information if you want to nail down where you're most likely to find the electron and the energy it's going to have within the atom. It's kind of like if I said to you, you know, 2 people in this room, they both live in Ohio. Okay, well, that's everybody. Okay, well, these 2 people they both live in Richfield. Okay, well, that's still a lot more than just 2 people. But these 2 people live on the same street. Well, we still haven't, but in other words, to differentiate the 2, I'd actually need the number address. In other words, I need more and more information to nail down exactly where we're most likely to find that person and the energy associated with the electron. Now, these pieces of information, we would say the electron is quantized with respect to energy in 4 different ways. These little pieces of information that nail down the energy of the electron and where we're most likely to find the electron are referred to as variables within these wave functions. You know the variables x and y, right? Okay, these functions have variables as well, and we refer to these as quantum numbers. And there are 4 quantum numbers. Each quantum number gives us another piece of information of where what the energy is going to be associated with the electron and where we're most likely to find the electron. Now, where we are going next is we're going to be examining what these quantum numbers are, what they represent, and how the electrons are arranged within an atom. We'll do that first thing tomorrow. So that's what we're going to pick up. So in here, 846, let's see. Who's in choir? Con's choir.
Choir's first period.
Oh, yeah. This is first period.
No.
Yeah,
No,
choir is
no,
choir.
that was our choir.
Oh, good. Kids for Kids, Project Love, Jazz Band, Pep Band.
This is tomorrow.
Ooh.
Oh,
Pep Band, ooh, you're going to be missing, and at 8 o'clock you're gone. So it's good that you're going to be taking it again tomorrow. Symphonic Band. Wind Assemble Band. Ensemble. Color Guard. Academic Challenge.
Oh, yeah.
Okay, you're going at 8.